Greetings and welcome once again to my new calculus channel. My name is John Gabriel. So, in this video over here, where I talked about the Hippias and the trisectrics, which was in 2017, I had just been homeless for about, I think it was 6 to 8 months, and it was developed in some library in San Jose, California, or off the Highway 1 coastal road, or I can't even remember where it was developed, and I don't really want to remember where it was developed because those times were really bad. But I did say when I developed that the ancient Greeks proved all these things without any knowledge of the sine or inverse sine series, which were discovered by Newton centuries later. They did not use Cartesian coordinate systems, and the geometric objects were not identified by equations. So I said, if I'm still around in a year's time, because I wasn't planning to be around, I shall reveal how they got these sorts and provide a fascinating glimpse into the minds of the most brilliant people who ever lived. I shall reveal what were their thought paradigms and what led to their ingenious proofs. But for now, I will state the ideas behind the trisectics. So that is what I did back then, okay? And for those of you who don't understand, this here actually represents a radius. So, it's to be able to make a radius of a circle, to be able to make the diagram bigger. So in this particular diagram, which I'm going to be dealing with, I've set it to 1, okay? And I'll explain the rest in a second. So I don't really need that. And I'm going to blow that away, make things simple. And now, by the way, the Greeks used chords, and Hippias used something called a kinematic curve, and you can read all about it here. And I'm going to show you how that works in a second, because that's what my applet does. And explain to you how to find a radical unit angle, and then how to use it in any one of the trigonometric ratios, okay? So choose kinematic curve, okay? Like this, kinematic curve. And as you can see, I've set A to 1, which is how I want it, and I've just zoomed in. Now, this here gives you the number of steps for the partition. So if you set it to 6 and you go over here, it will do 6 equal angles. 1, 2, 3, 4, 5, 6. Okay. And notice that it's still a right angle because the length of the sine line is square root 2, or approximately square root 2. Right. So what I'm going to show you now is that you find the angle using this geometric method. So you do one step, and you'll see that the radical angle is, it's very small, but it says 29886, okay? And that corresponds to 15 degrees in 360-degree measure, or pi over 6, or pi over 12, actually. Pi over 12 if it's 15 degrees. So how do we get the answer? So what we do then is we take this value that we found here, okay, and we convert it to the parameter. As you'll read about the parameter inside my article here, it's very well outlined. And it uses one parameter so that it has a seamless transition between angle and ratio. It's even the inverse is very easy to use, unlike unlike Newton's arc sine and arc tangent and all that nonsense that he came up with infinite series. This is dead easy, okay? And it gives you 100% exact results, whereas Newton's you have to iterate and you don't know whether it's accurate or not. And this is also a lot faster because it's done in a fixed number of steps. All you do is just put x, the value of x, in these formulas, and you're all good. So to get from the radical unit angle to the parameter, we just divide this value, which is, let's see, I'm not going to do the whole thing, 29885.8, and you divide it by square root 2, right? So divide it by square root 2, and you get 0.21132 approximately. And then in order to find the sine, the ratio of that sine, you just pass it to this function down here. So x is equal to this green parameter, and then you get the ratio, okay, which is this. So this ratio should correspond to the sine of 15 degrees. We've got degree mode, 15 degrees. Go to trigonometry, sine. Yep, It does, right? Look, see there? 25881. Okay, very good. So now, once we have the ratio, we can go from the ratio using this inverse formula back to the parameter and then back to the angle. Okay, so it's just an extra step, but it's very easy because it doesn't involve anything like infinite series. So now here you've got, and by the way, RA is exactly the same as arc sine. I called it RA because of radical angle units. So then you put the ratio parameter back in here again in this formula, and it gives you the parameter, which is the angle parameter. And then to get back to this, you just, instead of dividing by square root 2, you multiply by square root 2, and you've got the radical angle unit, which we found using Hippias's kinematic curve, not trisectics, the kinematic curve. Trisectics is something else, but I bunched all these things up together. Now, if you wanted to find any other angle, all you do is you just say what proportion of a right angle you want. So if you want, let's say, 1/15th, you type in 15 like that, okay? And then put it right at the beginning, and that should be 15 steps. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And of course, always the length of this blue line through one sweep is square root 2. And of course, if you go right back to the beginning, you take one step. This here would be the radical angle unit you would use. So you'd have to divide that by square root 2, okay? And then you would use that as a parameter to sine, as you see here, find the ratio, and then go back again if you want to get back to the radical angle unit. So this, by the way, is extremely important and extremely powerful, and it takes a genius to realize these things, okay? So nobody else realized these things. The ancient Greeks certainly didn't. They were working with chords, but they never even came close to what I revealed to you in this brilliant article. Now, don't be put off by the beginning of this article. These insults are meant at the morons of mainstream mathematics academia, people like Norman Wilberger, Gilbert Strang, David Ulrich, Jack Hazinger, all those fools. Okay, this is especially at Jack Hazinger, because he certainly didn't know that the sine series takes only radians as parameter. And of course, he didn't know that the sine of 0 over 0 is actually equal to 1, doesn't require limits, doesn't require any proof whatsoever. And how does that work in with these, using these new functions? Well, let's just see quickly, okay? So the sine ratio is, with these new formulas, by the way, okay, it takes a parameter x, and it's x over root of 1 minus 2x plus 2x squared, okay? 2x squared. So if we want sine x over x, like that, it means this whole thing divided by x, which means that this here is actually equal to 1 over this, right? 1 over that. And if we put 0 in here, we end up getting 1. So there's nothing about the bullshits of limits, and you don't have this typical crap that you find in the flawed formulation of calculus, where you've got x going to 0 of sine of x over x. This is in your face, Jack Hazinger, you little porky pig, okay? And I especially don't like Jack Hazinger because he retracted his critique and he did not apologize. And I feel very bitter about that. He needs to make a public apology and tell the world that he made a terrible faux pas. Anyway, not to carry on ranting. So this is what I didn't reveal to you in 2017. Now, just try to imagine how much else I haven't shared with you. Just try to imagine, because that's all you can do. I mean, you can't read my mind. You can't even know what is in the mind of a genius. Most of you are abject morons with no special mathematical ability. That doesn't mean you can't learn to do mathematics the right way. You can. And you can be better off if you do it the way I tell you, not the way your moronic mainstream professors and mathematics teachers tell you. Okay. Now, if you're not already a subscriber, become one. Click like on my channel because I have many, many enemies. Okay. I can't even, they're innumerable. So they're going to vote my videos down. Then become a follower on Academia, and I'll place a link given to this article once again. And if you have any questions, feel free to ask, not more than about one or two in the details section. Any comments, please spare me comments that are silly or drivel. I don't like reading crap. So just hold your 2 cents if it is 2 cents. If you have something to say it, and I'll read it, and I might even respond. Okay, that's pretty much it. My name is John Gabriel. This is the New Calculus channel. Till next time, goodbye.